Hello everyone, my name is Rodrigo and I'm here to present my article which is part of my master thesis research and it's called Nonlinear Parameter Estimation in Diesel Engine Simulation. I have written this article alongside with my supervisor Cesar Cunha Pacheco and let's start with a provocative quote. That's the provocative quote by George Box, which is like a very important statistician from the 25th century. He said once, all models are approximations. Essentially, all models are wrong, but some are useful. However, the approximate nature of the model must always be borne in mind. So all models are wrong, all of them have errors, all of them have pros and cons. And let's talk about the internal combustion modeling. Essentially, I have took four different approaches for internal combustion modeling. The first three are like they use like CFD, they use like uh, jet phenomena, and they have like a high level of computational cost, and they're like very slow and so on. But based on our research, we have selected the zero-dimensional heat release function, which pretty much uses like ODEs to describe the phenomena of the internal combustion engine. Uh, doesn't require so much of a computational cost. It's like very straightforward. It's like very fast. And internal combustion modeling is like very useful not just for the academia, not just for students. It's also very important for industry. Let's talk about softwares, commercial softwares. Uh, there are like several commercial software for internal combustion modeling. We have Ricardo Wave, AVL Boost, which actually uses a zero-dimensional heat release function. Diesel Archie, Los Alamos National Laboratory has their own Kiva. This is like a very important laboratory in the US. And here is the schematics of a diesel engine. We have the valves, we have the piston, which goes from bottom dead center to top dead center, and it's connected with a connecting rod, which goes to the crankshaft, and from each stroke, the piston go from the bottom dead center to the top dead center. Usually, diesel engines have like 2 or 4 strokes. In general, diesel engines have 4 strokes, and they are like inlet stroke, compression stroke, combustion stroke, and exhaust stroke. But here in this article, we are just going to discuss about the compression stroke. And following here, we are going to discuss about the model. This is the numerical model for a compression for the compression stroke of a diesel engine. As we can see here, we have two ODEs for temperature and pressure, and many parameters here, and we can solve those ODEs using numerical methods. And let's talk about a crucial difference, very important for the present article. So, we have the forward problem, which is like using a numerical analysis to solve the coupled ODEs as we have seen before. So we select parameters, we have the ODEs, and we use the Range-Kura algorithm to retrieve a pressure data for during the compression stroke. And first of all, we solve this so-called forward problem, and we create a pressure curve for the compression stroke, and we add noise. We add noise with a Gaussian distribution. Okay, and this is what we call synthetic data. Okay, and here uh, the main problem here is to solve an inverse analysis. What is an inverse analysis? We have this synthetic data, as mentioned before, which was generated by the Range-Kura algorithm. We have the numerical model, and we perform inverse analysis using the Levenberg algorithm. With this synthetic data, with the numerical model, we have an initial guess for the parameters, and after iterations during the Levenberg-Marquardt algorithm, we retrieve the initial parameters that we have used for the Range-Kura algorithm to generate the synthetic data. Okay, here we have the Diesel engine parameters, which we have used to create the synthetic data. And after, as mentioned before, we create the synthetic data using the Range-Kura algorithm. And we have here an initial guess, which is like 90% of the exact values for the initial parameters of pressure and temperature. As we can see here in row 1 is the are the exact values to create the exact values to create the synthetic data, and on the second row we have the initial guess, which is like 90% of those exact values, and the estimated values on the third row. And on the fourth and final row, we have the relative error from the retrieved values, which are described as estimated values on the third row. And as we can see here, the relative errors like slows less than 5% for both of the parameters. It's like a good result. And let's go further on the results. Okay, here are the pressure curve. Uh, on the on the blue on the blue points here we have the synthetic data, and the simulated data after the Levenberg-Marquardt algorithm is described with the red line here. As we can see, it's like a very good approximation. And on the right graph we have the distribution of the residuals. As we can see here, they don't have like a pattern of distribution, and We have performed some some tests regarding if it is a Gaussian distribution. We have used the QQ plot and the Shapiro-Wilk test, and both of them, the residuals passed as a Gaussian distribution. It's like very important for our results since we have added the Gaussian noise for the synthetic data, as we mentioned before. And going further here with the results, we have the results for the temperature. We have two curves here, which are like very close. The blue one is using the parameters from from the parameters from the synthetic data, and the red one is using the parameters after performing the Levenberg-Marquardt algorithm. Okay, and on the right graph, we have the difference between the temperature curves. As we can see here, roughly after minus 60 degrees, it starts to converge, and it's very it's a very interesting it's a very interesting result because as we can see here, there's like a change of pattern between after minus 60 degrees, and we need to have like a further investigation because as we can see here, the slope's like positive, but the concavity is like negative, and after reaching here the peak, it changes. The slope's negative and the concavity is positive. And after this change, it starts to converge. Uh, I'm going to discuss a further investigation in my master thesis regarding this mathematical phenomena here. And let's keep going on the future work for my master thesis. As I just said, a further investigation with the temperature curve. Of course, we have like experimental data, and we have proven that we developed the interesting tool for inverse analysis during the compression stroke. But the internal combustion engine doesn't have just one stroke. It has as well combustion stroke, inlet stroke, and exhaust stroke. So a further research using the four strokes must be done. And that's all for my presentation. I hope everyone enjoyed it. And let me go back here for the first slide. Uh, Here's my email address as well as my supervisor email address. You you can send me an email if you want to talk about internal combustion engine modeling. I'm up to talk, and thank you all.